Hello and welcome. In this video we're going to analyze the final form of the second order linear differential equation, which is the non-homogeneous second order linear differential equation. So far, and even in this lesson, we're going to focus on the differential equation that is roughly speaking of the form second derivative plus some function of t, some constant. I think we maybe have written some function of t, but we're just going to focus on the situation where that coefficient of dy dt is a constant. So I won't put g of t there, I'll just say g plus some constant times y equals 0. So that's what we've been focusing on, but in order for this to be non-homogeneous, we have some sort of function over here. Now we are referring again to these coefficients as being constant, and therefore we often refer to this as a non-homogeneous constant coefficient second order linear differential equation. So kind of a long term, but this makes it a very specific situation. So if these are functions, this method will not necessarily help us get any farther. But moving forward, we considered the spring mass model, which had two main forces. One was the force due to the spring, and so recall we have some sort of spring here, some sort of mass attached to it, and wherever we have displaced this spring relative to rest, so let's just say that that represents y equals 0, which is at rest, then if this spring becomes stretched out, then the force of the spring wants to act in the opposite direction of the displacement. So it's going to want to go that way. Similarly, if we compress this spring, then the spring is going to want to push it the other way. So there's this negative proportionality. And as we know, the farther you stretch a spring, assuming it doesn't distort, the more that you can feel that force getting stronger and stronger in the opposite direction. So the more displaced that spring is from rest, the bigger the effect of that spring force. Damping force is similar, but that's negatively proportional to velocity, meaning that if this mass is moving downward, the damping force is slowing it down. A harmonic oscillator can also have this thing called a forcing function, so this f of t over here, which essentially means that there's some superficial force applied to the system. So consider when you, if you've ever seen mattress testing, they take the mattress, imagine this is the mattress, and they have some sort of roller, some overhead roller that rolls this thing back and forth and applies pressure to those springs inside of that mattress. Also, think about the force of gravity. So this could be the force of gravity acting on the mass. So we're going to refer to this new force, f sub force, as some function, potentially of time. It could be constant. So our spring mass system starts to look like this. The right-hand side is non-zero, so this f of t makes this equation non-homogeneous. So to solve this, it turns out that we can already use some principles that we've learned, and this theorem, called the extended linearity principle, is what we get to apply here. So the beautiful part about this theorem is that as long as the equation is non-homogeneous and it has to be linear, we can apply this theorem. So let's just kind of state this. Suppose we wish to solve the above differential equation. If y sub h of t is a solution to the homogeneous differential equation, so set equal to 0, and y sub p is a particular solution to the non-homogeneous equation, so the only difference between these is that this includes the f of t in there, so we have to find the solution, the general solution to this homogeneous version of the equation, and then we find a guess, oftentimes by observing the structure of f of t and then formulating our possible guess for y. Then we can sum these together and we get our general solution for that differential equation. So solving the homogeneous version can be done what we've already done, and solving the non-homogeneous equation, we'll use the method of undetermined coefficients. We kind of guess the general form of a solution, and then we solve for that unknown. So let's take a look at an example. So here we already have the system built with the spring force, damping coefficient, mass, and the right-hand side is mass times acceleration. So this is gravitational force. And Here we have initial conditions, so the spring mass system is at rest, but it is actually moving into a compression because the velocity is negative, and the mass is 10 kilograms, and we'll assume that the gravitational constant is 9.8 meters per second squared. So if you multiply kilograms times meters per second squared, you get units of force, which is in newtons, which is exactly what all of these should be in. The artificial forcing function is the force of gravity on an object that has a mass of 10 kilograms near the surface of Earth. Okay, so that means that the first thing that we're going to do is we're going to solve the homogeneous version. So the homogeneous version will just be the second derivative plus 3y prime plus 2y equals 0. And so we already know that our solution to this is going to be of the form e to the rt, where r is unknown at this moment. So method of undetermined coefficients will help us find that. And the reason we know that this is a solution is because this is the only function, can't be sine or cosine, because if y is sine and the first derivative is cosine, and those two will never add up and combine to give us 0. But e to the rt, when you take its derivative, you get re to the rt, and you take its derivative, you get r squared e to the rt. And now making our substitutions in this equation, we have y double prime plus 3y prime plus 2y equals 0. And so once again, we can factor out e to the rt and see that the only way for this left-hand side to equal get a 0 product is if r squared plus 3r plus 2 equals 0. Now we can solve that however we want, quadratic formula, but if we do factor this, which of course this one factors nicely, they don't often do this, it factors into r plus 1 times r plus 2 equals 0, so r equals -1 or r equals -2. So what we've referred to as y sub h, our homogeneous solution, is k1 e to the -1t plus k2 e to the -2t. And this gives us two solutions, e to the -1t and e to the -2t, but by the superposition theorem, we can sum those two solutions to a homogeneous equation, and that forms a new solution. Now the non-homogeneous version. So now we need to consider the situation where the right-hand side is non-zero, and mass times acceleration, 10 times 9.8, will give us 98. So solving this now requires me to find a function that when I take its second derivative, I add 3 times the first derivative to it, and then add 2 times the original function to it, I get 98. Well, the only way for that to happen is y cannot be a function that is anything but a constant. And here's why. Let's suppose we let y equal t. Okay, well, that's already a problem because now I'll have 2t here, and then its derivative is equal to 1, and then its derivative is equal to 0, so 0 plus 3 plus 2t will not give me 98. So my guess cannot have a t in it. Same thing for like t squared. Well, that means I'm going to plug in t squared here, 2t here, 2 here, and there's no way that a constant plus a linear plus a quadratic will add up to 98. So the only way for this to happen is if y is equal to some constant. So let's go with it and see where this leads us. So that means that the first derivative will be 0, the second derivative will also be 0, and now when I substitute in my guesses, I have 0 plus 3 times 0 plus 2 times the constant equals 98. Perfect. So as long as the constant is 98 divided by 2, which is 49, this will be a solution. Okay, so that means that y non-homogeneous, which we'll call y sub p, this is a particular solution. There's no arbitrary constant that can be attached to this. The constant has to be 49. So you can just double check your work here. 2 times 49 plus 2, 3 times 0 plus 0 is 49. So our general solution will be y equals yh plus yp. And so y is going to equal k1 e to the negative t plus k2 e to the negative 2t plus 49. And we could always check our work. We could take the first and second derivatives of this and plug it into the non-homogeneous equation that we're trying to solve in the first place and see that it makes everything work out. So there's our general solution. Now, of course, we want to satisfy some initial conditions. So in order to do that, we know that our initial position, our position function is this one. I'm going to need the velocity function as well because I have an initial velocity condition. So y prime is going to be negative k1 e to the negative t, derivative of that first term, minus 2k2 e to the negative 2t, and then plus 0. So I know that my initial position is 0, and what we know is when we plug in 0 for the t's, we just get k1 plus k2, and then plus the 49. For the second equation, we're going to get negative 1, is our initial velocity, equals negative k1 minus 2k2. And we'll use Wolfram alpha to solve this and see what we come up with. And so when we insert this into Wolfram alpha, we get k1 equals negative 99, k2 equals 50. So we're now prepared to write our final solution, which is y equals k1 e to the negative t plus 50, which is k2, e to the negative 2t, plus 49. Now we want to see how this thing behaves and to see what happens. So let's go ahead and graph it. And we get something pretty interesting here. So initially, our spring mass system is completely uncompressed, meaning that at time 0, the position of the mass is at rest. Now, we know that we had an initial velocity that wanted to compress the spring. But the interesting thing is that the spring doesn't compress. It, in fact, stretches, and it actually stretches out to about 49 in the long run, meaning, and this is assuming a very elastic system. This doesn't have to be an actual spring in a mass. This could be some sort of vibration. So let's think about what's happening here. Let's kind of sketch this out. So we're saying we have this mass attached, and what's happening is this thing is attached right now. It's perfectly at rest. The initial velocity is wanting to compress this thing at a rate of negative 1 meter per second. But that's not a very, that's a pretty rapid speed, I suppose. However, let's think about the fact that we essentially have a force on top of this. So maybe what we've done is we've put some sort of 10 kilogram weight on top of this. So if I sort of put this 10 kilogram weight on top of this mass, well, the spring wants to pull this thing back up, but it probably is the case that the upward velocity just isn't enough to overcome the effects of gravity. So this thing has potential to want to compress, but what actually happens is this thing slowly droops down, and what happens is it comes to a new resting point where it ends up being 49 units of stretch. So basically this thing is going to kind of slowly inch its way down, at first kind of, well, I should say kind of rapidly, and then it'll slow down and come to a stop. So not a very interesting spring mass system. We have too big of a mass on there, and we could also analyze what would happen if we had different spring constants, etc. Now, one of the cool things to pay attention to is that the only difference between this solution and the solution for the homogeneous version that has no gravity assumed is if I take away that 49, now what happens is that, well, my initial conditions are off now, so that's something to consider. But now the spring mass system will return to rest regardless of the initial position. And the reason that's going to happen is because now it doesn't have the effects of gravity, it just has the effect of the damping attributable to any damping forces such as friction, etc. But now that we have gravity considered, its natural resting point of the spring mass system is 49 units of stretch. So hopefully that seems somewhat intuitive. Now let's consider another situation. Here we have an exponential forcing function. So notice that we have an exponentially decaying external force on the system. That is, the initial force on the spring mass system is large, but then quickly dissipates. We should observe that the spring mass system has some intense initial behavior, but that it then quickly returns to its normal behavior. So let's think about the size of this. So this has to be in newtons, which is equal to kilograms multiplied by meters per second squared. So you can kind of think about it as a similar to the force that we had up top, except this force is going to change over time. And if we look at the force, the F sub force, which is this function here, it's going to start off at time 0 at a force of 20 newtons. But as t passes, so let's just say after 1 second, this will be approximately 7 or 8 units. So this thing will really rapidly drop, and as t becomes infinitely large, this force really goes away. That's going to happen pretty quickly, because by the time you raise this to the second or third power, this force is now down here at 1 newton. So it'll have some initial intense behavior. Eventually, once that force loses its momentum, then we're just going to be focusing on the spring mass system. Now here's the thing, this force could be intense enough to where, because this thing is damped, it will just damp a lot faster than it would if we didn't have that forcing function. Okay, now we already know y sub h, so we're not going to derive that again, because y sub h is just going to be the solution to the homogeneous equation y double prime plus 3y prime plus 2y equals 0, and we solve for that up above. The only difference between these two equations is the non-homogeneous forcing function. So this is still going to be k1 e to the negative t plus k2 e to the negative 2t. All we have to focus on now is just the non-homogeneous component. So the non-homogeneous component is going to be now postulating a guess for y double prime plus 3y prime plus 2y equals 20 e to the negative t. Now the only way for these three functions that are just derivatives of this original to add up to an exponential is for the original function to be exponential. So my guess is going to be y equals something, I don't know what, but something e to the negative t. That coefficient is undetermined. I'm going to determine it. So let's take its derivative, which will be negative c e to the negative t. And let's take its second derivative. I'm going to make a quick change to this function for a reason that I won't go into here. I'm going to make this e to the negative 0.5t. So that won't affect anything that we've done already. We'll have a little bit of a problem if we leave it as negative 1t, but let's make it e to the negative 0.5t. So that means our guesses here are just going to have, I guess that will change. This will be negative 0.5t, and this will be negative 0.5 c e to the negative 0.5t. And the second derivative will be positive 0.25 c e to the negative 0.5t. And so what would have happened is if I left it as negative t, these three would have added up to 0, and so we would have had to update our guess. And I don't want to get into that right now because it's just a detail that is better left for another time. So now we plug these guys in. So we have y double prime plus 3y prime. So that's going to be 3 times negative 0.5 is going to be negative 1.5 c e to the negative 0.5t. Plus 2 times 0.25 will give me plus 0.5 c e to the negative 0.5t equals 20 e to the negative 0.5t. Now again, you could see this as factoring out an e to the negative 0.5t. What I see here is that plus that have to equal 20 e to the negative 0.5t. So, I'm sorry, just have to equal 20. So this coefficient plus this coefficient plus this coefficient has to equal this coefficient. So 0.25c minus 1.5c plus 0.5c has to equal 20. And again, if you factored out an e to the negative 0.5t, then you'd see that the coefficient of the sum of these will just be this expression down here. If I add these together, this will give me negative 0.75c has to equal 20. And double check my work there. I think that seems right. So c is going to equal 20 divided by negative 0.75, which comes out to about negative 26.7. Negative 26.7. Not exactly, but close enough for our purposes here. So that means we've just found that y sub p has to be, with its now determined undetermined coefficient, negative 26.7 e to the negative 0.5t. So we're going to add these two guys together to get the general solution. General solution is going to be k1 e to the negative t plus k2 e to the negative 2t minus 26.7 e to the negative 0.5t. So as t approaches infinity, regardless of what these coefficients are, all three of these terms are going to go to 0. You raise something to a negative power that's large enough, it will go to 0. So to find our initial condition, we need the velocity function, which is negative k1 e to the negative t minus 2k2 e to the negative 2t, and negative 0.5 times negative 26.7 comes out to about 13.35. So plus 13.4 e to the negative 0.5t. So now I substituted my initial conditions, and so the same initial conditions as the last problem, just so that we can compare these and see how they behave differently. So this one's going to get 0 initial position equals k1 plus k2 minus 26.7. So t is 0. And then initial velocity is negative 1 equals negative k1 minus 2k2. But now when that's 0, we'll have plus 13.4. So going to Wolfram alpha, and we get k1 equals 39, k2 equals negative 12.3. So our final solution is going to be y equals 39 e to the negative t plus, or I should say minus, 12.3 e to the negative 2t minus 26.7 e to the negative 0.5t. So we're now ready to graph this. Again, we can see that as t approaches infinity, these three terms will all go to 0. And here's what we get. So we do see that there's that initial condition that the spring mass system does successfully stretch, or rather compress, and then returns back to rest. Now that's as opposed to not having that term in there. Again, wrong initial condition, but this thing rapidly returns to rest. But with that term, we get a little bit of an oscillation before returning to rest. In fact, we can see that it still does its thing, it still goes to rest, but because of that forcing function being applied, we do get a little bit of a hiccup here. So if we wanted to model this, we could call this f of x over here. And just to see what that spring mass system would do, let's plot the point 0, comma f of t. And now we'll say t equals 0 and set our slider for time from 0 to about, we'll say, 15 seconds. All right, so I'm going to zoom this in a little bit here. We'll go from time 0 to about time, we said we wanted to go about 15, so there we go. So there's that initial movement. Watch this little dot here as we press play, slow this down a bit, make it move forward just once. So there we go. Not super exciting, but if you're designing a suspension system, maybe that is very exciting. Great, so there we have our final solution. And let's take a look at one more situation. So I hope these have been kind of intuitive situations to give us a little bit of a sense of what's going on. Here, the reason I think that we were able to get that oscillation that initial desire for that mass to move into a compression state. Here it was blocked off because the mass was heavy and it was constant. So notice that our force here was 98 newtons, a constant 98 newtons. But our force down here, 20 e to the negative 0.5 t, that initial force is only 20 newtons, and it quickly dies off. So I think that even though there is something that is sitting on top of that mass, if you will, another mass on top of the mass, it sort of starts to diminish. Maybe it starts to evaporate slowly, but just to give you a little bit of a visual, I'm saying that. Now, the other kind of common forcing function that you'd see mainly in something like testing mattresses is you have something that is constantly rolling across the mattress back and forth, or constantly applying downward pressure and upward. So it could be moving sinusoidally. So we already know the homogeneous solution for this one, so I'll just go ahead and state that. Y sub h equals k1 e to the negative t plus k2 e to the negative 2t. Now, the non-homogeneous has if we can recall from when we were solving non-homogeneous linear differential equations that were first order, whenever we had a sine or a cosine on there, our guess had to be of the form a sine 2t plus b cosine 2t. And the reason for that is this issue of this first derivative here, that if you let y equal sine of 2t, then its derivative will involve cosine of 2t, and its second derivative will be back to sine of 2t, negative, but notwithstanding, if a sine of 2t plus b cosine of 2t is used, then each of these gets a derivative, and so the sine becomes a cosine, the cosine becomes a sine, and it just sort of helps everything work out. So y prime is going to be 2a cosine 2t plus minus 2b cosine 2t, and its second derivative is going to be negative 4a sine 2t, and this one will be this one should have become sine up here. So derivative of cosine is negative sine. And so the derivative of that would be negative 4b cosine of 2t. So plugging in our guess into the non-homogeneous differential equation, second order, which is this guy, we get y double prime is negative 4a sine 2t minus 4b cosine 2t plus 3y prime. So I'm just going to triple the coefficients on both of these, make it 6a cosine 2t minus 6b sine 2t. But that's going to get added to twice y, which is doubling the coefficients, will give me plus 2a sine of 2t plus 2b cosine of 2t. So that's just this last term here. And all of that has to equal cosine of 2t. All right, so let's think about this. We have cosine terms. So this cosine 2t plus this, that's not a cosine, it's a sine, plus this cosine of 2t plus this cosine of 2t has to add up to the coefficient of cosine 2t. Now that's a 1 right there, so I can say negative 4b plus 6a plus 2b has to equal 1. Now what about the sines? Well, there's no sine on the right-hand side, but I could write plus 0 sine of 2t. And so what that would enable me to do is to say all of the sines, their coefficients have to add up to 0. So I'll write negative 4a minus 6b plus 2a equals 0. Now I'm going to put this into Wolfram alpha, but I'm just going to combine terms here. Negative 4b plus 2b is negative 2b, so I have 6a minus 2b equals 1. And negative 4a plus 2a is going to be negative 2a minus 6b equals 0. So solving this Wolfram alpha will give me those coefficients, I get A equals 3/20 and B equals -1/20. So let's think about what we just found. We just found the coefficients for our non-homogeneous solution. So we have A, so y particular equals A, which is 3/20 sine of 2t, minus B, or plus B, which is -1/2 cosine of 2t. Now that's our y particular. To solve this non-homogeneous, we have to add together the homogeneous and particular solutions. So our final general solution will be y equals, get ready for it, k1 e to the negative t plus k2 e to the negative 2t plus 3/20 sine of 2t minus 1/2 cosine of 2t. Wow, that's a whopper. So that's our general solution. And now, of course, we need to go and solve another system of equations to be able to get our k1 and k2, our arbitrary constants. Now remember, our k1 and k2 are based on our initial conditions. So this guy here is our position, and we need our velocity. So taking the derivative of this, which fortunately isn't too bad, just a lot of terms. And then we'll have plus 2 times 3/20, which would be plus 6/20 cosine of 2t. And this will give me 2 times -1/2, which is -1. But then the negative of that will be sine of, so plus sine of 2t. Okay, and now we're ready to go ahead and plug in our initial conditions. So as we do that, we just need to be careful here, lots of terms. So 0 equals, 0 is our initial position. This will be k1 plus k2. Sine of 0 is 0. Cosine of 0 is 1, so I'll just have -1/2 times 1. And then my initial velocity, that initial velocity wants to compress the spring, minus k1 minus 2k2. Cosine of 0 is 1, so plus 6/20 times 1. Sine of 0 is 0. So here's the system last system I need to solve in order to get my solution. So here we have those coefficients k1 and k2, -3/10 and 4/5. So I can say y equals -3/10, it's k1, e to the negative t, plus k2, which is 4/5, e to the negative 2t. And now I get those sine and cosine terms, which are 3/20 sine 2t. And then finally, I have -1/2 cosine 2t. This should make for some interesting behavior. Let's go ahead and take a look at the graph. So here we have it, and on first sight, you almost miss it if you don't look carefully. But we do notice this abnormal behavior here at the beginning, and that is likely due to the fact that we have these exponential terms in there. So initially there is that by itself, without these non-homogeneous terms, again, barring the initial condition is a little bit different, here we would just get decay if we didn't have that sinusoidal forcing function. But because we do, we see that this initial behavior is probably due to those two terms there, because for small x, these guys matter quite a bit. But as x gets larger and larger, as time gets larger and larger, these two terms dissipate, and now the forcing function is really just causing that spring mass system to oscillate. Again, think about this as an armature pushing up and down on that spring mass system. Even though there's damping forces, the fact that there's something pushing up and down on that mass is what's causing the mass to continue moving despite the damping coefficient. So if we took a look at this point once again, and we kind of modeled it over time to see what happens, well, pretty normal at this point, but thing to note is just that initial behavior is a little more erratic. So it only dips down a little bit for the first oscillation, but then it resumes normal operation pretty quickly. And so here's just a better version of that graph so you can see that first initial distinct behavior very clearly. So hopefully there's a lot of intuition behind this as you're thinking about these things and reviewing what these forcing functions do. They're just applying an artificial force to that spring mass system, more generally called a harmonic oscillator. So this could be a swaying building, a vibrating bridge that cars are driving across. Anything that involves some sort of oscillation can be modeled by this situation. Of course, we're just looking at the spring mass system as just this contraption, but this applies to many different areas, including electrical circuits, where we can think about things like inductors and capacitors as contributing to this sort of oscillatory behavior.